warahmatullahi wabarakatuh. In this video, we go to the next chapter, which is Introduction to Internal Force Convection in Cylinder. So this is introduction, and after this, we will go to internal force convection. So previously, we already learned about the external force convection, where we have I will change this first. So let's say we have tubes. Okay, we have tubes with a diameter di, internal diameter, and external diameter d out. So previously, we already concerned our calculation. We do some calculation on the outer part of the tubes, where we have to find what is the heat transfer coefficient for the external force convection. If we can draw from side view, so we can see that previous chapter, we are concerning more on the flow, external flow of fluids from the tubes. Okay, now in this chapter, we are more focusing on the fluid inside the tubes or the cylinder. So here we have two conditions where we have number one is constant surface heat flux. Surface heat flux. And then second condition, we have constant surface temperature. Okay, we have these two conditions in order for us to determine the fluid exit temperature of the fluid. Normally, the question that deals with the exit temperature or surface temperature will falls under constant surface heat flux. Under the constant surface temperature, we have two conditions. So I change the pen first. Okay, we have two conditions where the number one, we have laminar. Okay, developing entrance region, where we have laminar flow. And then the second one, we have turbulent. So under this condition, we will assume that the flow is fully developed turbulent flow. Correction on this slide. So previously, I've already mentioned that there are two conditions. One is constant surface heat flux. And second is constant surface temperature. So I've mentioned that under constant surface temperature, there is two types of two conditions. for laminar and turbulent flow. Actually, it is not only for constant surface temperature, but it is only for both. It is for both. Okay, both of these we will find what is the developing laminar entrance region, and then fully developed laminar flow, or a fully developed turbulent flow. This will be teach, and you will understand on how to calculate these properties. Calculate this in order for you to determine what is the Nusselt number. Then you want to find what is H. Okay, my correction is on the condition under the constant surface temperature. I've mentioned that under constant surface temperature, there is two Roman, two more condition. It is actually for both. Okay, constant surface heat flux and constant surface temperature, we have turbulent and laminar flow. Okay. So normally, under the constant surface heat flux, the info required for us to solve the heat transfer coefficient or heat transfer problem for the internal force convection, we are required Ts, T exit, and T inlet. So what is this temperature? So here, when the fluid enters to the tube, we have T inlet, and the fluid exit to this tube will be T exit, and then we have T surface inlet. Okay, because we are dealing with internal force convection, therefore the T surface temperature is inlet surface temperature. So when we have the constant heat flux here outside of this tube, constant heat flux such as electrical heater, so there is a constant heat flux to the tubes. So this tube will be heated, and then the fluid inside will be heating. And this temperature is actually normally in the constant surface heat flux problems, T exit and T inlet will be given. Therefore, you have to find what is the T surface. So under these topics, you will understand on how to calculate the T surface temperature. So what if we have to go to the constant surface temperature? So under the constant surface temperature, you will not have this heat flux to the system. So the heat flux will be, there will be no heat flux here. Then, for example, you have your pipe, and then under the fluid will be submerged into the fluid, where the fluid is at 0 degrees Celsius, for example. So under this condition, here we have constant surface heat flux. Okay, so our focus on this constant surface temperature is normally to find what is the heat transfer coefficient. So you will know what kinds of information you need in order for you to determine the heat transfer coefficient under constant surface temperature. So that is all that you will learn in this chapter. Okay, so laminar and turbulent flow in tubes. Flow in a tube can be laminar or turbulent. So everybody knows about this because you already learned in the fluid mechanics, because the fluid flows in the pipe will experience laminar or turbulent flow. Okay, depending on the flow condition. Fluid flow is streamlined and thus laminar at low velocity but turns turbulent as the velocity is increased beyond a critical value. So the fluid is streamlined, which means that it will goes in a straight path line. okay, and then that is laminar flow. Whereas for the turbulent flow, the condition where the fluid layer will flows crossing the other fluid layer. Okay, so the critical value. So previously under the external force convection, you already know that the flat plate has the critical value, where when you calculate the Reynolds number beyond the Reynolds number calculated beyond the critical Reynolds number, it will be considered as turbulent flow. Whereas for the value of the Reynolds number below the critical value, it will be considered as laminar flow. Normally, laminar flow is at low velocity compared to turbulent flow at high velocity. Okay, so the laminar to turbulent flow, there will be a region where where we know that that is a transition region. So before it turns into turbulent flow, it will goes to laminar at the beginning of the pipe, and then it will turns into transition region, and then goes to turbulent region. Okay, so normally what you learn in the fluid mechanics, the Reynolds number for the laminar is below than 2300, but for the fully turbulent flow, uh, Reynolds number which greater than 4000 will be considered as a turbulent flow in fluid mechanics. Yes, the turbulent flow will start at 4000, but to become fully turbulent flow, the Reynolds number will be beyond than 10,000. Okay, you have to remember, to become fully turbulent flow, the Reynolds number must be greater than 10,000. If you calculate your question Reynolds number, then you get 11,000, then you will assume that the flow is fully turbulent flow. Okay, and then let's take a look at the Reynolds number equation. Okay, so I change the white. So Reynolds number equation previously, okay, we know that Reynolds number equation is V and D. I change it DH, hydraulic diameter divided by V, which previously I've already mentioned that Reynolds number, okay, is equal to VLC over V. This form of Reynolds number is the same as this Reynolds number form. Okay, but I change here is DH, which here is hydraulic diameter, whereas here is characteristic length. Since we deals with the circular shape, so therefore I change it to DH. So DH here will be diameter. So since we are dealing with internal force convection, therefore DH will becomes DI. Okay, another form of Reynolds number is rho V D I over mu. So you may use either VDI over V or rho VDI over mu. These two forms of Reynolds number can be used. If you can substitute the value of the Reynolds number, so we want to find, there is another form, okay, actually there is another form where you do not have a, you don't want to calculate what is the velocity of the flow, therefore you may use the equation of 4 m dot divided by mu pi d. So actually this equation is the same as this, because if we want to calculate what is the velocity, we have to get the value of the velocity from mass flow rate. Therefore we substitute the equation for volumetric flow rate to find the V, and then it will become this equation here will becomes this. So you may use this equation or this or this. So all these three is the same. Okay. So the entrance region. So when the fluids enter to the pipe, so there will be an entrance region. Okay. So consider a fluid entering a circular pipe at uniform velocity. So because of the no slip condition, we know that when the fluid enters to the cylinder, okay, or the tubes or pipes, there will be a no slip condition around the pipe wall. So the fluid layer that nearest to the pipe wall will be stick to the surface, and this is what we call as a no slip condition, and velocity at that region or at that point will be 0. So as the x increases, these effects that stick, okay, we know that the fluid layer stick to the surface will affect to the adjacent layer. So it will increase as the x coordinate increases. So if we combine all those affected fluid layer, we will get a boundary layer region. So the boundary layer region is actually effects of the viscous shearing forces caused by the fluid viscosity, because there is fluid that stick to the pipe wall and then it will affect to the adjacent layer, and this affected layer will be increased as the x coordinate increases. Okay, when we combine all those layers, so here is a boundary layer region. And what about then? What about the layer where we do not, where the viscous shearing force does not affect to this layer? Which means what region we call where the fluid does not affected by this fluid layer? Okay, the no slip condition. We call it as a irrotational core flow region. Okay, and it will approach to the center of the fluid, where at beyond of the hydrodynamic region, here we have a fully developed region where all the layers will be affected to the fluid that sticks to the surface, and the viscous shearing forces affected to the all layers, and this boundary layer will increase as the x coordinate increase, whereas for the irrotational region will be decreased as the x coordinate increases, and it will reach to the center of the fluid, to the center of the pipe, sorry. And then this is what I told you before. The thickness of this boundary layer increases in the flow direction until it reaches the pipe center. So the hydrodynamic entrance region, we have two regions here. We have hydrodynamic entrance region and hydrodynamically fully developed region. So the hydrodynamic entrance region is the region from the pipe inlet to the point at which the boundary layer merge at the center line. So here we can see that the boundary layer will increase and it will approach to the center of the pipe. Okay, for the hydrodynamic fully developed region, the region beyond the entrance region, which the velocity profile is fully developed and remains unchanged. Okay, as the x continues after this point, it will remain as it is, remains as fully developed velocity profile. Okay, so this velocity profile is parabolic in shape for a laminar flow, but somewhat flatter or fuller in turbulent region. So we know that the turbulent region, this layer will cross to the adjacent layer, so it can be crossed to the next layer. Okay, laminar flow will goes like this. Okay, fully developed velocity profile. Okay, this example is for laminar flow because the shape of this velocity profile is in parabolic manner. Okay, as we can compare to the velocity entrance region, we know that when we do the thermal entrance region, the fluid layer will remain as it is. Okay, it will remain as this kind of form as the x coordinate increase. For the temperature profile, as we can see here, for the velocity, the fluid layer will stick to the pipe wall and the velocity at the pipe wall will be 0 meter per second. But if we compare with the thermal entrance region, the temperature at the fluid layer will be the same as the surface, because at that layer the conduction process will be occur, and then it will transfer the temperature or heat to the center of the pipe, and it will increase the temperature profile here as the x coordinate increase. Okay, the thermal boundary layer along the tube is developing, and the thickness of this boundary layer increases in the flow direction until the boundary layer reach the tube center. Okay, the thermal entrance region, we have thermal entrance region here, and then thermally fully developed region. This region is actually the same as velocity boundary layer region. Okay, and thermally fully developed region, the region beyond the thermal entrance region, in which the dimensionless temperature profile expressed as Ts minus T divided by Ts minus Tm. Okay, it will remain unchanged. So this is how the thermal entrance region, if you are required to draw the thermal entrance region, it will be the same as a velocity boundary region where the boundary layers will increase, or the thermal boundary layer will be increased as the x coordinate increases, and the temperature at the pipe wall will be the same as the surface. Okay, and it has two regions, thermal entrance region and thermally fully developed region. So at the hydrodynamic fully developed region, we know that each of these fluid layer will have a different velocity. So we have velocity at this point. I will change to red. So we have different velocity at different points. As the y increases from the center to the pipe wall, the velocity will be different. So it depends on the y. It depends on the position of the fluid layer. So the fluid layer will be different at different layers. Okay, so at this point, for the hydrodynamically fully developed, the velocity is equal to UR. Okay, for the thermal fully developed, so this is the equation that we derive, that will be derived, and then is equal to 0. So therefore it will becomes, we know that the x is increases, and as we can see here, it is much easier for you to, when we do some integration and derivation, we know that the hx heat transfer coefficient is constant for fully developed flow. So we can see from this figure. So for the hydrodynamic entrance region, we can see that the hx is different, and it will reduce as the x increases. and after it reaches to the point where the fully developed region starts, and it will become constant. So this graph is actually represent all this derivation. Okay, derivation, and we know that the hx is constant, and it can be shown by this figure. Okay, so this is developing region, and then fully developed region. So at the fully developed region, heat transfer coefficient will be constant. And then to calculate the entry length, so we know that here from the figure, we know that there is hydrodynamic entrance region and hydrodynamically fully developed region. To understand how long that the entry length takes place in your flow, therefore you have to calculate this LH. So for the laminar flow, when you calculate your Reynolds number and you get laminar flow, then you can use this equation, and it depends on what types of region that you want to search. Either it is hydrodynamic or thermal entrance region. So for the thermal entrance region, it will be LT, L length for thermal entry regions, and laminar flow. And you have to plug into this equation in order for you to calculate what is the thermal entry length for the laminar flow. Okay, normally you will get this LT much more greater than length for your tubes in your question. So if you get the turbulent flow, then we have to calculate what is the entry length of that turbulent flow. And we know that the entry length is where the laminar flow takes place. And in order for you to determine the entry length for the turbulent flow, you have to use this equation, thermal approximate. And then LH is approximately to 10 D, 10 diameter. So let's say you calculate your Reynolds number and you get your Reynolds number is about 4,000, and then you have to calculate the LT. Sorry, this is LT turbulent. You want to calculate what is the thermal entrance region for your flow or question flow. Then you have to substitute 10D, and you have to compare with your tubes of pipes length. Okay, so this figure represents the Nusselt number for a turbulent flow. Okay, the Nusselt number are much higher in the entrance region. So as we can see here, the Nusselt number is higher for the Reynolds number. As the Reynolds number increases, and the Nusselt number will be higher. It will depend on the Reynolds number for the entrance region. Okay, the Nusselt number for the uniform surface temperature and uniform surface heat flux condition are identical in the fully developed region and nearly identical in the entrance region. As we can see here, as it approaches to the length of 8 for this number 1, Reynolds number 2 times 10 to the power of 5, we can see that the Nusselt number is constant when it reaches to the certain region. So this region is actually fully developed region. Okay, and this region is actually entrance region. This region is entrance region, and then this is thermally fully developed region, where we know that at the thermally fully developed region, the Hx will be constant, and it's same with the Nusselt number, where at the thermal and fully developed region, the Nusselt number will be constant. Okay,